Okay, so I'll begin this week. So this week I want to embark on two ideas for the next 2 weeks. One is I want to introduce hypothesis testing on the topic of linear regression. So in this, we'd like to test if it's a good fit. So you want to test if model is a good fit. That's the broad idea. And we devise various ways of how to test this, understand this, and so on and so forth. The other thing I'd like to do is sort of a classification step model. So it's called the one-way analysis of variance. So there are two things that I'll do over the next 2 weeks. And I'll try and mix it up with some R and coding as well. So the first thing is you'd like to sort of start with, let me go back to the idea of simple linear regression and just do a very simple test. Try and show you this. You may have already seen, but let's do it slowly again. So let's start with simple linear regression. And so now, what did we do there? We had a model like y is equal to x beta. Sorry, let me do beta naught plus beta 1x plus epsilon. So epsilon was the error. And we assumed that epsilon was going to be normal with mean 0 and variance sigma squared. Let's say known, let's say for the time being. Then we had the idea that E of y given x equal to x is going to be, the mean is just going to be beta naught plus beta 1x. That was the idea, that was the model. So we should just call this as x perhaps. So make sure that's. So now this is a simple, and we had methods of which how to estimate beta naught and beta 1, and we'll come to that in a second. Now, let's for the sake of argument, suppose I want to compare another model with this. So what's the easiest model to compare? So let's say another model I want to compare this model with another model. So to provide another model, let me provide the simplest model of it all. Let's just say that I just fit the mean function. Okay, so let's just say a very simplistic model is when beta 1 is 0, that is E of y given x not equal to x is just the same beta naught. No matter what little x is, at same value as capital X, I always put beta naught. Right. So what would you do? You would have data points, data points y1, yi, xi, yi, let's say. So you have data xi, yi, 1 less than equal to I less than equal to n. And then to do the least squared estimate, what you do is you'd find beta naught such that summation. So your everybody is the same for every x. So it's just y naught minus beta naught squared, I equal to 1 to n is minimized. Very good. So now, but then you know that this answer you can easily solve by calculus. Otherwise, you already know that beta naught hat in this case would be just y bar. Right? That's the answer. And then you'd go and say, okay, fine, now let me go and try to do the residual sum of squares. The residual sum of squares, that's going to be equal to what? Summation I equal to 1 to n, yi, and I'm putting the same fit beta naught everywhere. So it's y minus y bar, the whole square. That's the so This turns out to be just like we called before. I'll just call it as the sum of squares of y's. So here, here you can easily see that in this case. So if I know, I only know, since I have y bar already available to me, I only need to know n minus 1 of the y's, right? And so I have this as this is not free entire data set. It's governed by only n minus 1. So in some sense, what you could say is that this has, this has n minus 1 degrees of freedom. And the reason being that is it is n minus 1. The minus 1 is because y bar governs the information as well. Right? So if I know y bar and I know n minus 1 of the y's, then I can get over this whole. So this is the, let's call this model 0. So let's call this as model 0. So if you do model 0 in the simplest form, you get this is estimate, and the residual sum of squares is given by this particular number right here. Now let's go back and do the same thing. Let's go to our old model, original model again, our linear model. Let's call it as model. So what our model was, E of y given x equal to x was beta naught plus beta 1 times x. Very good. So here we can do the same thing again. We know how to estimate beta naught, beta 1, and we have done that many times before. So let's just write this down again. What will beta naught hat be? Beta naught hat, beta 1 hat in this case by. So let me write down. So the idea is to minimize, to find beta naught, beta 1 such that you want to minimize the residual sum of squares. That is, you want to minimize the sum of yi minus beta naught plus beta 1 xi, the whole square, right? And the data is just and the data is just given the same data, xi, yi, 1 less than equal to I less than equal to that. Very good. Now this here also we found out that if you minimize this, beta 1 hat is just sum of squares of xy divided by sum of squares of xx. So the same thing as, I'm writing a little bit fancy way, the same thing writing it as the stuff. Summation I equal to 1 to n of xi minus x bar and yi minus y bar, the whole thing divided by summation I equal to 1 to n of xi minus x bar, the whole square. That's what beta 1 hat was. And we found out that beta naught hat, you could solve it by just looking at the equation. Look at the equation, it passed the line y bar minus beta 1 hat x bar. And that's what beta 1 naught hat was. So in the integration case, right? And this you could just go and take a data set, and you could go and compute this whole this number. So in this case, what are the residual sum of squares become? Here the residual sum of squares became, if you do the computation, you would just get SYY minus SXY the whole square divided by SXX. This is what the thing was. And just to be more precise with this is just SYY was just summation y minus y bar the whole squared, I equal to 1 to n, minus this person is xy, so it's just the same thing as above. So it moves across a little bit. So we take this across, let me bring this down. Copy this. Down, paste it a little smaller. Yeah, and I put the top guy as whole square. There you go. That's what I got the residual sum of squares. Very nice. But here you can see, I know y bar and x bar, you can check. Like the previous argument, you can check this RSS has n minus 2 degrees of freedom. Something to just check a little bit. This one can also verify by hand. We did last time, some days back as well. Very good. So then we came up with this. So the difference between sum of squares in the previous one, in this RSS here, let's call this as equation 1. Equation 1. Let's call this as equation 2. So what's the difference between 1 and 2? The difference between 1 and 2 is the reduction in the residual sum of squares due to enlarging the mean function from let's call this as model A. Let's call this model A to original model. Let's call this model our model. Let's call this as model A, and this model is, let's say, model 0. So because we enlarged the model from 0 to A, one had a higher degrees of freedom than the second one. Right. So the reduction in residual sum of squares due to enlarging the mean function. So one way to understand is what is the sum of squares due to regression, right? So in some sense, let's write this down properly. So what is the sum of squares due to regression, or let's call it as model A. Model A versus 0, right? So that means all I do is take the sum of square, residual sum of square I got from model 0, I subtract it from the RSS, right? So the first, that means this is the same, I'll just call it as SS reg is equal to. So the first one I just got SYY. And the second one I got SYY minus SXY the whole squared by SXS. This is the difference I got the two. Right? So if you subtract the two, what do you get? You will just get SXY the whole squared by SXX. That's what you. That's the sum of squares due regression, right? Because that's one. And this one, so this is the difference in degrees of freedom from 2.1. The first one was n minus 1. The second one was n minus 2. So this guy is going to be n minus 1 minus n minus 1, n minus 2. So let's write it down. So here, simple exercise to check, that is the degrees of freedom for SS reg. What's it going to be? So the first guy had this guy had n minus 1. This person has n minus 2. So this guy, if I subtract the 2, I just get n minus 1 minus n minus 2. So I get n minus 1 minus n minus 2, and I just get 1. We want degree of freedom for simple regression. So this is something called the analysis of variance table, but we'll come back to that next time. But as of now, let's just sort of keep this in mind, that the sum of squared due regression has only one degree of freedom. Very good. So now let me try and understand some simple fact. Suppose this was large. Suppose this was large. That means the mean function beta naught plus beta 1x provides a significant improvement for the mean function over the simpler model 0. So this is equal to saying that beta 1 is different from 0, and it's not constant as the original model. Very nice. So let's try and write this down. So let's try and write it down. So now, this is what's called the F test. So I'm going to call it F test. So the idea is the following. What's the idea? The idea is, if SS reg was large, right? That is the difference between this one and this one was not the same. That means then the interpretation is that model A, that is model A that we had in mind, that is E of y given x equal to x, which was just beta naught plus beta 1x, was better whatever better means, was better or more significant or showed significant improvement than just the mean function. That is when just model 0, which was E of y given x equal to x, was just beta naught. Okay. So that's intuitively clear, right? If it was larger than this is what happens. Right? So that means the regression showed significant improvement was the thing. So this is kind of equivalent to saying, this is like, if you think a little bit, this is equivalent to saying beta 1 is not equal to 0. This kind of equivalent to saying in the model beta 1 is equal to 0. Right? So that means E of y given x equal to x is not constant in x according to the first model. And according to the second model, E of y given x equal to x stayed constant as x variable. So that's how So to formalize this, we must know to judge, this is important intuition to have. But the question now is, how large is too large? Or how large is significantly large? That is, how can I make a judgment call on this? So can I tell you, like, okay, if this is reasonably large enough, then it's thrown away. I will keep it. So it turns out this is something that we'll try and derive at some leisure at some point in time, or you may have seen it already before. That is this quantity turns out to be distributed like f up to a certain scale. So we'll have to check that in some sense, and how is it connected to f distribution. With that, we can sort of understand if SS is large, then this sort of thing is.